In this video, we're going to introduce sequences and some of the things that we can do with them. So what's a sequence? Definition. A sequence is just an infinite set of objects here that I'm calling A0, A1, A2, all the way up to AN, but then also past AN onward into infinity. It's a sequence of objects where each object, AN, is associated with, or sometimes we say indexed by, a distinct natural number, n in n. We can think of this natural number as describing the order. So if n is 1, for example, that's item number 1 in the sequence. If n is 2, that's item number 2 in the sequence, and so on. So you can think of sequences just as sets that have an ordering to them. So here's an example. Here's a sequence of integers. So the sequence 1, 3, 5, 7, and keep going. Here's another one, 1081, and then I keep going forever. This is the sequence of all odd natural numbers. This is all odd natural numbers, elements of the set of natural numbers in ascending order. This is a sequence that has an order to it, and it goes on forever. Here's another one. 1, 2, 4, 8. And then I go for a while. Here's another one. 5, 12 is an element of this sequence. And then I keep going on forever. This is the sequence of all powers of 2. Technically, all the non-negative powers of 2. So here are two sequences. A sequence is just a bunch of numbers that goes on forever. We have some notation for this. So the notation that we use for sequences is as follows. Notation. So instead of just writing out all these numbers or even using the dots, what we're going to do is we're going to write just a single element, a subscript n. We're going to put it between curly braces, and we're going to say that n ranges through all of the natural numbers. So this notation is a shorthand for writing a0, a1, a2, etc., an, etc. We don't have to write that out. Instead, we just say, okay, curly braces on either side, a sub n in the middle, nothing special about the letter a, it could be b sub n or something else. And then we subscript here to describe what the set is of all the possible indices n. And usually we're focusing on the natural numbers, including 0. So where do sequences come from? Well, one place that we can get sequences, one way we can generate sequences, is by generating them from functions. So here's the sequence that we saw, the sequence of all odd elements of the natural numbers, which we can write this way for short. We can write down a function that describes each element, a sub n. So here, a sub n has a formula, so I can describe it as a function of n. And this formula, there's many reasonable ones, but here's one. 2 times n plus 1. Okay, if I were to check that, I would say, okay, here's the 0th element of my sequence. If I multiply 0 by 2, I get 0. I add 1, and I get 1. That checks out. Here's the element number 1 of my sequence. That's 2 times 1 plus 2. That checks out. Element number 2, if I multiply 2 by 2, I get 4. Add 1, I get 5. 3, and so on. So I can check that each element of my sequence here corresponds to a possible input n that would generate the corresponding element of the sequence. Here's another one. So I can have a sequence 1, 2, 4, 8 onward to 5, 12 and into infinity, where here b sub n is my name for the elements of this sequence. And here, in this case, b sub n also has a formula, so I can write it as a function that I'll call g of n, and its formula is 2 raised to the nth power. So here, 2 raised to the 0th power is 1, 2 raised to the first power is 2, 2 raised to the second power is 4, 2 raised to the third power is 8, and so on. So sequences are infinite collections of objects. Usually in this class, they're infinite collections of numbers that we can index, usually with the natural numbers, and we can describe them, among other ways, in terms of functions. In addition to describing sequences with functions, I can also describe sequences recursively. A recursive definition of a sequence, or a recursive description of a sequence, is a formula that tells me how to compute the next element in the sequence using some function of the previous elements of that sequence. So we can think of f as a recipe here. It says, if I want to know the next element in the sequence, take a look at the previous ones, do some kind of computation, and then get the result. In addition, we also need an initial condition. We need to know some of the initial values of the elements in the sequence, because if I don't know the value of a0, for example, then the formula won't help me to find the value of a1. So let's do some quick examples. So if I consider one of our previous sequences, so 1, 3, 5, 7, and onward, this is the sequence of all odd positive integers, and it has this functional definition. If I want to specify this sequence, well, there's lots of ways to do it, but here's one. The initial condition is going to be simply the first element of the sequence, so that's a0 equals 1. And then my recursive formula, to get a recursive formula, what I need to do is I need to take the elements that I see and ask myself, hey, how would I get to 5 from 3, for example? How would I get from 3 to 1? Here, I see, oh, it looks like there's a difference of 2 between each element. And so I can also say, hey, the n plus 1 element, to get it, I can take the an element and add 2 to it. And this works for all n in the natural numbers. Similarly, here's another example. If I look at my example of the powers of 2, here my initial condition is going to be a0 equals 1 again. And my recursive formula is going to be, hey, I get the next element of this sequence by looking back at the previous element and doubling it. I'm going to multiply by 2. So I'm going to say 2 times bn again for all natural numbers n. So just to be clarify here, my RF is the recursive formula. So my recursive formula, RF, right there. I can have more complicated formulas that require multiple initial conditions. So here's one more example. This is a famous example, the Fibonacci numbers. So in the Fibonacci numbers, my sequence is defined Fn plus 1. So the n plus 1 Fibonacci number is the sum of 2 previous Fibonacci numbers. So this time I need to incorporate 2 elements of my sequence in computing the value of the next element. Because of this, I need 2 initial conditions. And so my initial conditions, in this case, this was my recursive formula. And my initial conditions are typically specified as f0 equals 0 and f1 equals 1. And this gives me the Fibonacci sequence. If I want to calculate more values of the Fibonacci sequence, I say f2 is equal to f0 plus f1, and that is equal to 1. f3 is equal to f2 plus f1, which is 2, and so on. So I have multiple ways to describe sequences. I can do it either by giving a formula that will give me every single element of the sequence That's sometimes called a closed form. But I also have recursive descriptions of sequences where I describe what happens in the next element of the sequence based on what has already happened in prior elements of the sequence. Both of these are really important in computer science applications, and converting between them is a really helpful skill.